hello. I perfectly understand if some of you left. Some of the stuff that I'm going to talk about, you probably heard it already 100 times. So it's okay. I'm basically going to talk about a couple of things. I'm founder of hackerspace, a local hackerspace in Tallinn. I've been running it for 2 years now. And over the years, I've accumulated knowledge about Python for more than over 10 years now. So there's some tricks and tips which I've learned which maybe aren't that straightforward. And sort of like latest experience that I maybe want to share is like I'll talk a little bit about async IO in Python and draw some parallels to the Linux kernel development book which I had recently skimmed through because of different reasons. And of course, talk a little bit about some of our projects, what we have done at our hackerspace. So, we're going to start off with a shameless hackerspace promo. So we started 2 years ago, as I said. It's sort of a mix of a hackerspace, makerspace, co-working space. It's located in the Technopole Science Park. Address is Academia Day 21/1. I think, how many of you have been there? Yeah. So the rest you're always welcome on Thursday, 6 o'clock. And basically why I created that place was that I was having my master's degree in Berlin. I spent 1 year in Berlin. I visited different hackerspaces that are in Berlin. Berlin has a lot of hackerspaces, like 30, more than 30, I guess. And those hackerspaces have different emphasis. You could find just a place simply only for like retro computing, where they collect old computers. We also have our tiny section of retro computing, some of the stuff we brought here as well, which you can see behind the curtain. And some of the places solely focus on manufacturing stuff, like Fab Labs. Well, I think Fab Labs originated from US actually, from MIT. So in a Fab Lab, usually you would have devices to cut wood, metal, to do welding, stuff like that. And since we have a lot of people who just want to hang around with the other guys, we also have a place which you could call a co-working space. You can just come here with your laptop. We've got really fast internet, but I guess in Estonia that's not an argument anyway. And we occasionally host Python Code Club as well. So I think Torgeir wanted to have it in November. So you're welcome, always. And basically over these 2 years, I think I've managed to get everything done. Like everything that I wanted to do, and I imagined that would have to be there is there. And I'm glad that as of today we've got about 40 paying members, and it covers all of the expenses and it functions as a non-profit organization, etc. So I'm really happy about that. And some of the latest news is that we've got also now an isolated room for dusting and painting stuff. So that we built that one in summer. And we also have now laser cutter, which was something that I didn't even imagine we would get so soon. But we struck a deal with Protoscope, Marty from Protoscope, so we have a deal that they can host their laser cutter there because they don't have really a place for a laser cutter in their office. And in exchange, our members can make use of the laser cutter and cut whatever they need for themselves. And I'm also glad to say that we finally made contact with the Estonian Radio Amateurs Union, or what's the English translation, I'm not sure now. We had guys coming over from there, and we're going to have a radio amateur exam on the 17th of October. So I guess some of you who have read something about radio amateurism think that it's sort of extinct hobby. It sort of became extinct because of the internet, you could say. Because before the internet, how would you reach people across the globe? You would use hand radio for that. But I would say nowadays there's an interesting shift there again, that from cybersecurity perspective as well, what are you going to do when internet goes down? And I mean like really, really goes down. That or 4G connectivity is gone, how are you gonna talk to each other? So if you want to meet fellow Doomsday preparation enthusiasts, you can come to the radiometer exam because you'll find people like that there. So people who are preparing for that situation where everything doesn't work, you can still use ham radios to talk to each other over short distances, but also across the globe. We finally got the promotional video clip done, so if you open up the hackerspace website, you see a video which explains where is the door, because for a long time that was a really big problem, because people would come to the building and then call me like, hey Lauri, where's the door? So we've got our hidden entrance behind the building, and the video illustrates where it is. And it also shows a bit about the facilities that we've got there. But I guess this sort of actually concludes what we have been doing with hackerspace. Come and visit on Thursday, 6 o'clock. That's the open doors day. But this also brings me to the next step. So what am I going to do? And for a long time I've been thinking, what should I do next? And it's sort of sad, but basically I started looking for a new job. And I applied to multiple places, and while doing that I was looking like what kind of a job I should be looking for, because to be honest, I feel like I never had like a real job. I've been doing random shit for past 15 years, I think, just to learn about things. But to actually have a job, I think I've never really had a job. And then I was like looking for different positions on Glassdoor.com. And I sort of filtered out stuff that I would be interested in. And I guess Python was one of the keywords. I sort of ended at this one. I did this actually retrospectively because I already knew what the keywords are. And the funny thing is that those poor system administrators are really underpaid, which basically means that manual labor isn't really appreciated that much anymore, because system administration essentially is a manual job. You log into a server, you apply updates, you reboot the server and hope that nothing breaks, right? But if you add coding into that mix, you get something that resembles rather site reliability engineering. And this basically doubles your salary as well. So these numbers are in San Francisco, in dollars, base salary over the year. So you can basically do a division by 12 and convert it into euros. Usually those people get a whole lot more because of bonuses and stocks and whatever. And I guess I can mention that the companies that I was applying for are like in top 5. And basically now got offers from some of the companies, and I'm now figuring out which one I'm going to pick. But I guess the point here is that if you are thinking like what you should learn next, then machine learning definitely is the way to go. I think I can honestly say I don't know anything about machine learning, and that's something definitely that I want to brush up on. I'm going to get some books, read what's going on, because all of the hackerspace stuff, I basically didn't have any time to read about machine learning and what is going on recently. So, and since Python is a central component in machine learning, I guess, this means that basically Python is becoming, how would you say, more and more appreciated if you know Python and know how to use modules written for Python. And the third one, the data scientist, statistics, and this very closely, again, associates with machine learning, I guess. But these top 3 are definitely the positions that you might want to chase if you want to get paid well. Yeah. And during the preparation for the interviews, basically for the whole September, I've been just doing interviews. And for the preparation for that, I was reading a lot of books about Linux in general, and it sort of dawned on me that, well, we have a lot of programming languages, but basically what most of them do, they just wrap C library functions, and those library functions just invoke system calls from Linux kernel. And I think it was mentioned in one of the Quora threads that what many companies expect, especially in the top 5, they expect you to know how the underlying operating system works really, rather than how a particular programming language works. And I guess I can give you like a sort of a brief overview, what might help you if you want to pursue a position in those companies. So there's also some of the things which I wanted to know more about, and I'd like to share here as well. So let's talk a little bit about system calls. I guess, how many of you know what is a system call? We've got some people, that's nice. So, but I guess most of you are into web applications, right? How many of you have something to do with web applications? Yeah, it's like almost most of the people. So you know the higher level, but you don't know what's going on deep inside, right? So I'll try to explain a little bit about that. So the classic Unix networking model uses forking to handle multiple requests simultaneously. Okay, let's try to put it in simple English. When you have a network application, like a web server, it could be Django running inside UWSGI or something like this. When a connection comes in, what the program does, it makes a copy of itself and handles it in a different process. That's essentially what forking means. Forking means that you're telling the operating system, please make a copy of this running Python instance, and we'll handle the client in one of the halves. So later on, POSIX threads were bolted on. POSIX threads basically means that within one process you can have 2 stacks running simultaneously, or even more. But we'll see later on that in Python that doesn't really give you much of a benefit. But the main idea here is that with both of those approaches, if you use multiple processes to handle multiple clients, or if you use multiple threads to handle multiple clients, it doesn't really scale well with long-lived connections. And I guess we could say that the web has a lot transformed from what we had 20 years ago. 20 years ago, you would basically go to a web server, put in a request, I don't know, PHP would render a view of a particular forum page, spit out the HTML to you, and that's it, right? But that's not the case nowadays anymore, because you want to use Facebook chat, right? The Facebook Messenger. But in order for the Facebook Messenger to work, you need to have a connection which is open all the time to the server, so the server can send you the message at an arbitrary moment. So we've sort of switched from polling the website for changes to having the server send you the changes instead. And this doesn't work well with the previous approach, really. And so at some point we had Node.js pop up, which said that, okay, we'll forget about forking and threads. We'll just do an event loop, handle everything inside one process, and we'll talk about the event loop in a moment. And in reality, actually, we have a mix of all of the above. If you actually, I was just, during the preparation for this presentation, I was looking how Nginx is written. Nginx is actually a mix of all of these. You have multiple event loops running inside multiple threads. So the real life is actually a mix of many things. And one of the other thoughts I had here was that when they came up with the Unix networking model, that was, I think the word fork was introduced in 60s. So it's basically more than 50 years old concept. So we didn't have multi-core and multi-processors computers existing back then. So a lot has changed also in the hardware, which should be reflected in the software as well. Okay, I could talk about the abstract stuff a lot here, but I'll just instead show you some code, try to explain what's going on. So when you write your Django application, somewhere inside Django, you have code that looks probably something like this, but hopefully not anymore really, because that's the old way of doing things. So that's the so-called Berkeley Sockets API. And It has its roots in the Unix operating system from a long time ago. Funnily enough, Microsoft copied that code base from BSD. So in Windows, you have exactly the same interfaces in use. And what the Berkeley Sockets API does is that it basically sets up a socket. So in this case, I guess I can a little bit explain about the constants that are being used in this code. AF_INET refers to IP networks, so anything that uses IP packets. Because at some point in time, we also had something else besides IP packets, like IPX and some other weird stuff, which isn't really used anymore. And sock_stream refers here to the TCP running on top of IP. So it's like TCP/IP stack in essence. I would actually skip the long one in the middle. This just allows you to run the program multiple times. Otherwise, the first instance of the program would sort of lock up the socket for the program. You wouldn't be able to restart this. And once you have the TCP/IP socket set up, you would bind it to a particular IP address if you have multiple network cards in the server, and to a port number. 000 in this case means that connection can come in from any network interface that is in this particular computer, and it would expect it to come to the TCP port 8080. So this basically gives you rudiments of web server, something that binds to port 8080 using TCP. And the sock listen function would actually tell the kernel that, okay, we have bound to all of these interfaces. Can you now start actually the server? The argument 5 here would refer to how many sockets, how many incoming connections would be dispatched to the accept call if you have multiple threads or multiple processes running on the same code. But in case of a single thread instance, it doesn't matter here really. And then you basically have an infinite loop. So if a connection is accepted by the server, you attempt to read 2000 bytes or 2 kilobytes of data from the socket and just send it back. This is like your classical example of an echo server, which just responds back with whatever is sent to it. And then it closes the connection. And then it will go back to the accept syscall, which would wait for incoming connection and serve that one again. And you can actually just copy-paste this, run it in your Python interpreter. You can use for testing, you can use telnet, you just telnet to localhost, type text there, it will echo it back. So what's the problem with this code? The problem with this code is that the receiving syscall here is blocking. It's blocking until it gets some data from the client transmitted to the server, which means that if you have another client connecting at the same time, they would be starved for that resource, and the server would eventually, I think, it would time out, I guess. So how would you handle multiple clients? So the classic way of doing this is that you would, for instance, after accepting a connection, you would call fork syscall, which would tell the operating system that, okay, make a copy of this process. In one of the copies, I will deal with this particular client, so the other one could continue back to go back into the accept syscall, which would wait for another client to connect. And this means that the receive syscall could block. The client might be just doing some goofy stuff there, but it wouldn't block the additional connections being handled by the program. So let's say this is like the classical way of doing things. There's like many variations how you can use the fork. Apache Web Server, for instance, spawns a bunch of processes before actually going into the loop. So you would have the fork happening before the loop itself. But fundamentally, you still have the same problems. So I guess if you've read about threads, then you could ask like, okay, fork is so 80s, so why can't we use threads? So in C programming language, the threads help somewhat. But even then, the C10K limit is there. C10K basically says that using these classical networking models, you're unable to serve more than 10,000 connections from one box. And you can find here multiple reasons why that is happening. Is because resources are allocated for every process. And eventually, what your computer will be doing is just context switching between processes. As if you have 10,000 of them running there, it will spend an awful lot of time just switching between processes which are handling now these 10,000 connections. Now, we can finally get back to the Python aspect of all of this. So in Python, we have the global interpreter lock. How many of you know what is global interpreter lock? It's the scary one, right? Some people know. Okay, so in Python, if you're using threads from the threading module, you look at the API, everything looks beautiful, right? And then you write your program and you try to run it on I don't know how many cores AMD has nowadays. I think it's like 64, right? Or something, getting close somewhere. It's getting ridiculous anyway, right? So you would expect that it runs like 64 times faster than it does without using threading. But actually that's not the case, because all of the Python statements are actually evaluated sequentially, simply because of the global interpreter lock. And the reasoning is quite simple there, is that in order to have consistent behavior for data structures that are used by the Python, like dict and list and all of those, in order to make them behave consistently, you don't want those data structures to be accessed simultaneously from multiple threads. So due to this, it's actually a property of the C Python implementation. So Python itself, you could argue that it's actually like a standard for the language, and you can have multiple implementations of the language. So in particular, this applies to C Python. There's some other implementations where that's not the case. So you might be asking, what is the use of, or what's the benefit of threads in Python then? Well, the benefit becomes apparent when your program is actually using is spending most of the time in kernel space, which basically means that it's waiting for input-output to happen. It's waiting to read a file, waiting to read from a network socket. So you have benefit there. But I've seen many libraries, for instance, Python imaging library. Last time I checked, that was though some time ago, it didn't support threading correctly. So you say that, okay, I'm going to write a Python script that resizes a bunch of images, right? You wouldn't get the benefit out of that, because it wouldn't correctly handle the global interpreter lock. Some guys made a fork of the Python imaging library, called it Pillow. In that one, it actually worked correctly. And in the past, I've used OpenCV and NumPy. Both of them also handle global interpreter lock correctly. So you get actually the benefit of using threads there. But for many applications, like if you do string manipulation in a Python program, you don't get much benefit from threading at all. So this is something that is not very obvious, I guess. I guess it's technically written in the documentation, the way it behaves, but I guess most people don't really get it, that these are the implications of it. So I guess you might be asking, like, what are the alternatives then? So, well, we can use the sockets in the non-blocking mode, which basically says that if you try to read from a socket, it will return immediately. And a slightly more complex example, which actually supports multiple clients, looks like this. So I guess you might think, what the hell, why is it so complex? But let me try to explain it to you. Maybe it helps a little bit. So the beginning of the code is the same that I had in the initial example. You would set up a socket, you would bind it to a port, you would start listening on the port, and then you would go into an infinite loop, which would use the select syscall. Select syscall is kind of interesting one, which is explained in depth in the Linux kernel development book. The select syscall is basically used to tell the kernel that I have a bunch of network connections, please tell me which one has some activity going on there. So you send the list of those connections to the kernel, and it will tell you which ones have some activity. Is there bytes to read? Can you write some bytes to it? And if there is nothing going on at all, it will just stall. So you get a listing of those sockets, and here where the management nightmare comes in, you will just get an arbitrary list of sockets. And now you have to start figuring out what is what. So if the if the object that you got is a socket, you would have to accept a connection from it. If it is already established connection, you would have to read from it. So it becomes much more harder to comprehend what is going on here. And I guess that is the main reason why the asynchronous programming or non-blocking programming hasn't been adopted for a long time, because it makes the code much more complex. And there's a bunch of other applications there as well, which I'm going to discuss in a moment. And I guess this is also the reason why it took so much time to get these concepts built into the programming language itself, because it happened last year when async and await keywords were actually built into the Python programming language itself. So we've had actually the event-driven networking engine twisted from 2002. So this is now 15 years ago. They started doing asynchronous networking programming already 15 years ago, but the way it looked like was something like this, with probably a little bit nicer packaging, but the concept is the same. And Tornado web server has been doing this since 2009. But it took like 10 years to get these concepts rooted into the Python programming language itself. So in the summer, I think, or in the spring, I was looking for, like, do we now finally have some web development framework that actually supports the native way of programming those applications? And yes, if you want to look into it, we've got Sanic framework. It's very much like Flask, but it uses the async programming instead. And yeah, I think now we're like finally, I think they have had enough time finally to juggle all of the different options, how they would do it in the programming language itself, and we have finally arrived there. And this is how what would be the equivalent of the previous immensely complex code would look like in async programming. It's much more condensed. It sort of already resembles like the initial code that we had in the beginning. It looks pretty much like this one, right? But it uses the built-in await keywords and async keywords, which are now part of the Python programming language itself. Okay, let's try to explain a little bit what's going on here as well. So we have the function definition for the handler, which is executed when you have some activity on the sockets. So you get actually the sockets passed to the function using these reader and writer wrappers. These are, they look like sort of file objects. You can read them and write to them. And below here, we've got the event loop by initialization code, which basically asks the built-in async IO framework to get or start an event loop in the program, and it would register this callback function into the event loop, which would also do internally all of the binding to the all of the network interfaces on port 8080. And it would run this infinitely, basically. So what's actually happening now behind the scenes is that the async IO framework starts up the loop. If there's a connection coming in, it will handle all of that. You can actually have multiple connections to this program, but it will be running inside one process, using one thread only, but it would be multiplexed correctly. So you can have multiple connections up to the same program, and you wouldn't be starved for the clients wouldn't be starved for additional connections. So let's try to dig a little bit deeper. The async code, in essence, is no more sequential. So let's try to see what happens if you have multiple clients connected to this program. What the handler function does here is that it would tell the async IO framework that, okay, I'm expecting 2 kilobytes of data on this socket. Please wake me up when that happens. But you don't have to do explicitly this. This is sort of implicitly happens in the background there. So every time there's an await keyword, a function called with a await keyword, it in essence means that it tells the async IO framework that I can go to sleep now, and you can deal with other clients at the same time. But the thing is that the code execution is not sequential in that sense that it would be blocking here, but rather than this code will be suspended and another code for another client will be executed instead. So comprehending this gets kind of tricky because I've been used to writing sequential blocking code, so everything kind of straightforward. It just goes from top to bottom, right? Occasionally with loops. But now it gets intermingled with the other ones which are running at the same time. From a kernel perspective, what's happening behind the scenes is that in order to actually achieve this more than 10,000 connections per box limit, in the past, programs have been using the select syscall, which I showed earlier, right? But the select syscall, since you are passing the list of the sockets, and if you have 10,000 connections up at the same time, this means that you're passing a huge list of connections to the kernel and asking it to figure out what is what, right? So this doesn't perform well because the kernel has to inspect the list all the time. And on Linux, there's actually epoll syscall, which does it much more efficiently. You register the sockets before, and you have just one syscall which tells the kernel to look up which ones have activity. If you're running Mac, you have a KQ framework inside the kernel, which does basically the same thing. And this will enable the software to achieve the low complexity for polling the sockets. And this way you can actually have, from your ordinary laptop, you could easily serve 10,000 clients, no problem. And since like the 10,000 connections limit was sort of fixed some time ago already, because we have Nginx which uses async programming, the async web programming frameworks are coming up. The next goal is the 10 million connections per box. Because if you look at the hardware from like Moore law perspective, it should be able to serve a lot of clients. And we've got the capacity there, but really nowadays the software is the bottleneck. And async programming is the precondition for 10 million connections, but if you dig into this stuff, it gets really weird. They're talking about now user space networking and having drivers running inside user space. You could have some weird stuff like Python loading Intel network card driver into itself and talking directly to the network card and bypassing all of the kernel infrastructure that has been built over the last, well, 30 years, I guess. So there's really weird stuff going on there right now, but if you look at it from a big company perspective, it kind of makes sense. If you manage to improve the performance of the software even by a couple of %, this means that you maybe don't have to buy a couple of 100,000 servers, right? Okay, we're almost there. The complex part is almost over. Won't torment you with this much more longer. So some things that aren't, again, maybe that obvious. If you try to write async code and actually, you go home, open up the Sanic framework documentation, I'm going to write a async web application over the weekend. And then you have this, just to dial down the enthusiasm, you should remember that the event loop doesn't play well with any traditional blocking code. So if you have somewhere in your code something that will block the execution, it will stall the whole thing. You'll have like connection dropping in elsewhere simply because of that one. So this is like one of the problems that have been criticized about async programming is sort of like everything or nothing mentality. That if you use async programming, this basically means that you will have to go with async version of Postgres driver and async driver for the MySQL database, and for LDAP as well you would use async drivers. So you cannot use the regular ones that are out there. And that might be a showstopper for some applications which rely on something that simply hasn't been implemented using async code yet. For me, for instance, I think I didn't find any Kerberos library that would do async I/O. So for a long time, the lack of such modules was a showstopper, and I guess that was also one of the reasons why Tornado or Twisted networks, Twisted frameworks never became very popular. It has definitely its own use cases, but it really never gained like a mainstream attraction. And you should also remember that any computationally intensive code that you might be running inside async code will also stall the loop and prevent it serving the other connections. So how do you overcome this? One option is that you would spawn a pool of processes where each one runs event loop, and you would dispatch the jobs between those. But you should always remember that the global interpreter global interpreter lock rules still apply there. So there's option to use threads for event loop, that you'll have multiple threads running multiple event loops simultaneously. But again, if you use modules that do not release the lock, this means that the whole thing collapses again. And if you don't use threads and you will use multiple processes, then this also means that you will have data synchronization issues across processes, because if you want to share data between all of the processes, you're back to square one, right? And again, you might find yourself again in a situation where every process is doing something, which blocks all of the events loops from executing, and still all of the connections would time out because of that. So I guess if you look at it at a larger scale, you probably might want to use some message queuing system to submit the long-running tasks into separate processes, because right now we're talking about 10 million connections per box, right? So I guess we're talking about larger installation anyway. So in such setups, you would use message queues anyway to dispatch long-running tasks into different machines and whatnot. Okay, did you survive this? Did someone learn something new about this? Yay, it was at least more than one guy. Excellent. Okay, I'll go back to some more fun projects. So, yeah, reading about the book was very useful, the Linux kernel development book. I highly recommend that. I always felt that when I was reading the book that, before reading the book, I always thought that, okay, Linux is so complex, there's so many features there, that I will never get the grasp of everything that is out there. But now looking back at it, it's like, well, that's all of it. So Linux isn't really that complex when you look at it from programming perspective. It's actually reasonably doable to understand all of the syscalls that exist there, see what kind of functions wrap those syscalls in your programming language, and to make the best use of the kernel itself. Okay, but let's continue with some fun projects. So I think last year I was showing one or multiple of these. So as I said, I'm the Python guy who does some obscure stuff with Python. So with the IT college students, we built robots that participated in Robotex. Last year we got second place. These are the robots in the middle, using OpenCV, NumPy, and a lot of interesting hacks to make it perform well. And yeah, so hardware there is basically a regular PC plus ESP32 microcontroller. And I think last year I was going into lengthy details about ESP32, so I'm not going to talk much about that. But we also finished with the Sumo robots, which use ESP32 microcontroller. So the Sumo robots were there behind the curtain that you saw during the breaks. Some guys asked, what's inside there? So it's basically programs that run Python directly on a microcontroller and use WebSockets to connect to a server. And the IT college students used it to teach kids how to do programming, how to program robots in general. And we had web interface programmed for the laptops, where you could either write Python code or just drag and drop these puzzle pieces, which would generate the Python code. It would upload the code to the robot, and the code would actually be executed by the MicroPython interpreter that was running on the chip itself. So that was kind of neat. So everybody who told me that, oh no, you cannot run Python on microcontrollers, I think I proved them wrong. So another one which I think I discussed last year as well, ESP8266. Nice piece of hardware. I think now it costs maybe less than €1 already. It looks like this. Again, another interesting piece of hardware that can run Python. So the MicroPython framework basically is a custom version of Python interpreter, which implements Python 3.6 standard to a large extent, and it runs directly on the hardware. So there's no operating system in classical sense here. Okay, internally it uses free real-time operating system, but you don't really see it from there. And I used it for a clock, which connects to an internet using Wi-Fi, syncs up the time with NTP, and then just displays the time on the digits. So I think all of the code that was running in the code is like less than 50 lines of code in Python. So these are some unusual things that you might find being done with the Python. And on the top there, that's a thermostat from our server room at our hackerspace. It also runs Python. And the interesting aspect there is that since you are already like acting on some data, so we would just use the thermometer to turn on and off the fan in the server room, you can also blast this information to some statistics collection framework where you could visualize all of that, which with traditional microcontrollers isn't that much possible because most microcontrollers do not have Wi-Fi built in, but the ESP chips do. Okay, let's show you something new as well. This spring we did another project with students, largely thanks to the help of Marvin. Marvin's there. So we had a company approach our hackerspace asking like, hey guys, can you build us a bunch of tanks? So they wanted make a IT exercise look more appealing to the management layer of the company. So there was a field, 4 by 4 meters, where the businessmen had the opportunity to drive with these tanks. So we had the tanks here during the lunch. I think many of you had at least looked what's going on there. So let me talk briefly how we did this. So you'll find a lot of remote controlled tanks online which have infrared and blow out steam when they get hit and whatnot. So, and some of them, they are quite expensive as well. So I thought like, what is the cheapest price we could do this for? So we had a bunch of these travel routers. They cost like, I don't know, $25 a piece. We put OpenWRT there. OpenWRT nowadays actually has a decent Python packages, so you can just do OPEC against Python. The router has an I2C bus, which is essentially like 4 wires to hook up other devices. And we found I2C motor controllers that was trivial to hook up to the router. And actually we spent most of the time, or Marvin spent most of the time, figuring how to do infrared. So there's a lot of code examples for infrared, but since it's very timing specific and it essentially has to be hard real time, you cannot really do it in Python. So we resorted into having 2 at the tiny microcontrollers handling the hard real time stuff for transmitting the signals and receiving the signals. It basically uses the remote control signals and expose it on the I2C bus as well. So basically, we hooked up a USB camera as well, so you can see the video stream from the tank. We used the AR0330 USB camera with H.264 encoder built in, so you get compressed video feeds straight from the camera. You don't have to do it in software, which was kind of neat. And then we just blasted it over the network to a laptop, which was receiving it. And I think the Python code eventually was quite small. We used a Python script for receiving the UDP packets inside the tank, like start streaming video and move the motor this way and that way. And we used GStreamer to stream the video. So GStreamer I would say has quite horrible documentation. But once you survive that, you can do a lot of interesting stuff. So basically, once you figure out how to write the pipeline in GStreamer, you can just tell it to take these 264 frames and blast them out using UDP packets on the network. And it worked surprisingly well. And then we actually spent a lot of time figuring out how to show the video stream. Because I initially considered actually using web browser, but the problem is that web browsers nowadays use TCP in most of the use cases. And the moment you lose one packet on a wireless network, this means that the TCP retransmit kicks in, so you have like a couple of seconds of delay when there's nothing happening and the user gets frustrated. So we quite quickly switched to UDP, so you just get some garbage frames in the middle if you lose some packets, but at least it doesn't stop. And I think we spent two evenings drinking beer and figuring out how to put the visuals on top of the video feed, which was actually oddly the most complex part. And we considered a lot of options with GStreamer and without GStreamer. And the most straightforward way to do this, in my opinion, is to use OpenCV. So OpenCV has a GStreamer plugin. You can tell OpenCV to capture video from a GStreamer pipeline, and then the GStreamer pipeline will take care of receiving the video feed and decoding it into an array on top of which you can draw arbitrary stuff, really. So this is how we did it, completely misusing, I mean, this is a travel router, right? So completely misusing the device compared to its original purpose, right? But it works surprisingly well, and I think it was relatively cheap as well. And I guess if you're asking, like, well, why don't you use Raspberry Pi? Well, Raspberry Pi uses actually a lot of power. So the power consumption with this was very low, and we could keep it up and running for like 6 hours, I think it was. Whereas with Raspberry Pi, it would probably get drained in a matter of hours. So the source code is actually on the hackerspace Git. You can download it there, or inspect what we did. And I don't deserve any credit for this, maybe only for like whipping the boys that they would get the things done in time. But Marvin and Marek deserve actually all the credit for this thing. I just wanted to show that what's inside. And now for something completely different. If you've seen Monty Python Flying Circus. I actually wanted to skip this, and I guess I'm running out of time anyway. I didn't originally plan to include it in the presentation, but since Virgo was so excited about this, I'll talk a little bit about this one as well. So one of the things that I've always wanted to do is build speakers. So I bought a bunch of drivers in the spring, and I spent quite a lot of time trying to figure out how do I cut the plywood for the speaker. And gradually the expectations for me grew as well. Like I wanted to have it really good quality, like how the box is put together and how it's finished. So, but the funny thing is that I've never learned how to use CAD software. I've never used AutoCAD or stuff like that. But while I've been doing random stuff with the CNC machine, I've actually tried to understand what the CNC machine does while it's cutting stuff. And I started reading how the G code is written for the CNC machines. If you haven't heard, the CNC machine is like you put a drill on a bunch of motors and just move it around to cut off the excessive material. And G code essentially is like list of instructions, move this way, that way, and also to do an arc would be like interpolated by the CNC software. So you just tell that do an arc and it will do the arc. And since I knew programming, but I didn't know CAD, and I knew how G code was written, I just wrote the library for that. So yeah, I mean that's how. That's how they say like, the site reliability engineering is what happens if you let the programmer to do a system administration job. This is what happens if you let the programmer to do a speaker design job. So basically what happens behind the scenes is that there's like primitives are implemented in the library, like remove a rectangle, remove a circle, stuff like this. and then it outputs a G-code that I just put it on my CNC machine and it cuts it out. So, yeah. I think that's it from the hackerspace. These are some of the list of some of the myths that I've faced over the years, what people tell me about Python. I mean, at least for myself, I've managed to debunk all of them. So, yeah, due to GIL, Python will never achieve high performance. I think that was the last one. So, with async programming, that's not the case anymore. Python is only a scripting language. That's again false. The beautiful thing about Python really is that you can gradually go from script into an object-oriented program. Python can't be used for big projects. During the browsing these interview questions for the jobs, I recently learned that Instagram is also a Python application. I didn't know that. So Instagram is, they say that it's 1 million lines of Python, which is a lot. So this is debunked for me as well. For a long time, I actually had trouble finding like what's a good example of a Python, like a large Python application. So I guess Instagram would be a good example here. Python can't be used for video processing. Well, it sure can be. You can use the GStreamer inside there. You can use OpenCV, NumPy. You can do a lot of cool stuff. Microcontrollers, debunked. Python doesn't scale. Well, that's maybe a bad one, but yeah. So I'm happy to continue using Python, and happy to see that there's a lot of more and more high-performance computing is getting attention in the Python scene. And I think in the end of the day, Python will simply be like this your orchestration tool to get things running. But what happens behind the scenes could be easily like a C++ library or whatever like that. So thank you for your attention, and. Yeah, since I talked about interviewing in the beginning, I guess I'll be leaving in 1st of November. So if you want to run a hackerspace, come and talk. We're looking for activists to take over the job. But if that doesn't happen, then I think we already have enough people to survive. But I would very much greet some crazy lunatic activists like I've been for the past 2 years. Okay, thanks.
Thank you so much. That was rich in information. Let's get to the questions. So, first question. How fast is really fast internet in hackerspace?
That's a good one. So, the incoming connection to our server room is 10 gigabits. Between the rooms is 10 gigabits. And if you get yourself a 10 gigabit network card, and you come with like a big ass desktop machine, then you get 10 gigabits straight to your machine. So I think you will not find any other hackerspace that can do that. How expensive were the tank parts in total? I think you could assemble the whole thing for less than 300 euros. Probably, if you get very tight, maybe even less than 200 euros. Weirdest thing you have seen done with sockets? There is a sendfd syscall in Linux which allows you to pass a socket from one process to the other one, which was like, what? Why does that exist? But think about it. You can do a lot of weird stuff with that. Have you tried Golang as it is popular for built-in concurrency? Yes, that was actually one of the reasons why I wanted to do this presentation as well, because once you use Go, I used it for briefly, but the way concurrency is handled in Go, it feels good. It feels like it fits. But again, I guess that's because you have one of the Unix founders there designing the whole language. So I think the experience he has accumulated over the decades pays off there, because concurrency is complex. Well, you're welcome. You're welcome as well. Any more?
Is it possible to program flight controllers in Python?
I guess it depends which controller you have there. But, I mean, like if you need something that is, how to say it, where people can die, then probably I wouldn't do it yet. But for IoT devices, I think it's great.
What would your ideal next job be like? What would you like to be doing?
I would like to have a job where I can, after 5 p.m. I can like stop briefly, because doing the hackerspace was like running inside a hamster wheel, you know? Yeah, sure, I can share that.
Okay, great. Thank you so much. A big round of applause.